In this video, we'll be doing some examples from section 3.1 of our textbooks, beginning on page 450. Question number 30 here is asking us to graph the function h of x equals 2 raised to the x plus 2 minus 1. We're told to begin by graphing f of x equals 2 to the x, then use transformations of this graph to graph the given function. Be sure to graph and give equations of the asymptotes. Use the graphs to determine each function's domain and range. If applicable, use a graphing utility to confirm your hand-drawn graphs. I'm not going to do that last part. I'm not going to bring my calculator into it. I'm just going to graph what I've been asked to graph. Well, to start, the instructions ask me just to graph 2 raised to the x power. Oh, I like plugging in minus 1, 0, and 1, because I know when I plug in a 1, I'll just get the base. When I plug in 0, I'll get 1, and when I plug in minus 1, I get the reciprocal. So here's the graph of y equals 2 raised to the x power. All right, now I was asked to graph the asymptote. Well, this has a horizontal asymptote at y equals 0. Well, looking at what's going on here, x plus 2 in the exponent, right? I've replaced x with x plus 2. That's a shift to the left 2 units. Minus 1 on the outside, that's a shift down 1 unit. So let's just go on and process that shift down. That's going to move my horizontal asymptote. And it'll now be at y equals minus 1. I want to talk about what I could do if I was asked to do this and maybe just wanted to plot points. When I think about the values of x I usually plug in, this is moved to the left 2 units, so I could just imagine shifting those x values to the left 2 units, taking 2 away from each one, which would give me these x values. Well, then I could imagine plugging them in and getting a y value out. Well, I plug in a minus 3, I get 2 to the minus 1. Minus 3 plus 2 is minus 1, which would be 1/2 minus 1 is minus 1/2. And I see what happened. My y value went down by 1. That's the downward shift. Plug in a minus 2, I get a 0, and I get 2 to the 0 is 1, minus 1 is 0, and again, we've gone down 1 unit. And then finally, that'd make that be at 1. Right, again, I plug in a minus 1, I get 2 minus 1 is just 1. Let's plot those points, and we'll have successfully graphed number 30 here. All right, minus 3, minus 1/2, minus 2, 0, and finally, at minus 1, I need to go up to 1. All right. Now, I was also asked to write down domains and ranges. Well, the domain for this exponential function is all real numbers, so the interval from minus infinity to positive infinity, and the range, well, just above that horizontal asymptote. So there's number 30, where we've successfully graphed the function h of x equals 2 raised to the x plus 2 minus 1. Next up, we're going to do number 32. That bears the same instructions, but this time we're just going to graph g of x equals 2 to the minus x. Well, I remember that when we replace x with minus x, we get a reflection over the y-axis. So I could just do that, but I'm going to imagine I plugged in those same old values for x that we usually do, just to see what happens. Well, I plug in a minus 1, but now it's 2, in the exponent 2 raised to the minus 1, so that's positive 1, so I just get out 2. Plug in 0, get out 1. Now I'd have 2 raised to the minus 1 when I plug in 1, and that'd be 1/2. Well, what used to happen at minus 1 now happens at 1. We have seen that reflection. And there's the graph of that function with a horizontal asymptote at y equals 0. The domain, again, all real numbers, and the range this time from 0 to infinity. Well, let's see, we've done 30 and 32. Next up, we're going to do problem number 54. Number 54 has me think about our compound interest formulas, which are stated in the instructions, but we're going to need to know those for our next test. All right. Find the accumulated value of an investment of $5,000. So that's our principal. For 10 years, so T is 10 years, at an interest rate of 1.56%, 0.0156, if the money is, in part A, compounded quarterly, so N is equal to 4. In part B, part B is quarterly, part A, semi-annually, so 2 up there, sorry about that. And then 2 more parts to the problem. Part C, compounded monthly, so N is 12 there, and D, that's where we're going to compound continuously. So no value of N, we just use the formula PE to the RT rather than the traditional compound interest formula. Let's go through these one by one and we'll find the requested dollar amounts. All right, A is equal to the principal times 1 plus the interest rate divided by the value of N, all raised to the N times T. So 2 times 10. In my calculator, I'll type in 20. $5,000 times 1 plus 0.0156 divided by 2 raised to the 20. Now, if you wanted to, you could type in 2 times 10 here. You could make your calculator do all the work, but be careful. On these older calculators, you have to use a set of parentheses there. All right. Well, here in part A, that means we get $5,840.59. Well, we're going to set up the same kind of equation here in part B. The only difference is the value of N is no longer 2. It's now 4. So in the exponent, I have 4 times 10. I'm just going to go on and write a 40 there. All right, so in this equation we had before, that becomes a 4, that would become a 4, and there's my new balance. So $5,842.36. 2 more parts to this problem, and then we'll try number 56. All right, 12 times 10, 120 there in the exponent. So again, we use our graphing calculators. All right, $5,843.54. And then one more part, that interest is compounded continuously. Well, I know what's really going on here. Every time N goes up, I get a slightly higher dollar amount. And then this is kind of, well, not kind of, this is the theoretical maximum. This is the most amount of interest I could earn. So it'll be the highest number we've seen so far. But I have a feeling it'll be pretty close to that one. So 5,000. Second, the natural log button to get that E in there, 0.0156 times 10. Oop. 500 and 5,000 are different numbers, so let's do that again, though I know I could just multiply that one by 10, but I like seeing all the correct buttons getting pressed in these videos. So there we go. 5,844. $5,844.13. All right. With that amount of principal, that amount of years, and that interest rate, that's the highest amount we could possibly ever have. That's the interest being compounded continuously. Let's take a look at number 56. Number 56 has us take a look at another interest situation. Suppose that you have $6,000 to invest. That is our principal. Which investment yields the greatest return over 4 years? So there's a value of T. 0.88% interest compounded quarterly. So an interest rate of 0.0088 with an N equals 4, or 0.9% compounded semi-annually. All right, well, there's only one real way to answer this, and this is to actually just find the balance in both accounts. All right, let's see. 4 times 4 would give me a 16 there in the exponent. All right, let's see. I get 6,214 and 72 cents. All right, next up. Still have $6,000 as a principal. 1 plus 0.009 divided by 2. And then the exponent, I have n times t, which this time's just 8. And I get $6,219.43, which that's your better account, not by a whole lot, but by enough to matter. So the account with 0.9% interest performs better over 4 years. All right. One more problem here that I wanted to do from section 3.1, number 66. Number 66 gives us an exponential function that's applied to a historical event. In 1986, there was a nuclear power plant in Chernobyl, Russia that suffered an explosion. It sent out about 1,000 kilograms of radioactive cesium-137. And we get a function here that describes the amount in kilograms still in the atmosphere in that area. So f of x equals 1,000. And then 0.5 all raised to the x over 30. X is measured as years after 1986. If 100 kilograms of cesium-137 remain in Chernobyl's atmosphere, the area is considered unsafe for human habitation. Find f of 80 and determine if Chernobyl will be safe for human habitation by 2066. Well, those are related because 1986 was when it happened. X is years after 1986, so 80 years after 1986 is 2066. So we're just asked to find f of 80. So this is really just about typing in an exponential equation to our calculator and getting an approximation. I probably usually just write 8 over 3 there in the exponent, reduce the fraction, but we can key in exactly what was given to us. And we get that there's about 157.5 kilograms. Make sure they got the units right here. Kilograms of cesium-137. Well, that's over the limiting value we were given of 100, so no. Chernobyl will not be safe. By 2066. All right, well, those are the problems out of section 3.1 I wanted to go over, and that's it for now.